1.5D will be all about radical equations. That is to say, equations with radicals in them, not necessarily, liberal equations. Now, unlike the two equation types that we've talked about in the past, rational equations and quadratic equations, where they needed special techniques. To solve a rational equations, you clear the fraction. To solve quadratics, you can use factoring and completing a square or quadratic formula. Radical equations need not any special techniques. The good news is, all you need is Algebra 101, inverse operations. If you see a plus 5, you do a minus 5. If you see a multiplication, you do a division. So all that it takes to solve a radical equation are inverse operations. However, there are some key ideas that we need to know. So we only need inverse operations to solve these types of equations. We need to know that radicals, aka roots, like square roots, cube roots, fourth roots, we need to know that radicals and exponents, aka powers, an exponent of 2, an exponent of 3, squaring, cubing, that sort of stuff, aka powers, are inverses. Those two ideas basically tell you what to do. If to solve a radical equation you just need inverse operations, and knowing that exponents are the inverses of radicals, to solve radical equations, we're going to be using a whole bunch of exponents. Easy peasy. But I'm going to add one extra little fluff or flair that's only specific to radicals. And this is sort of like my tip or my hint here. So I didn't do a bullet point, I did asterisks here. Do not use... Question? Anything I can clarify? All right. Do not use any exponents until the radical is isolated. Now, I put an asterisk there because it really is not a universal law. If I didn't listen to this third bullet or this asterisk here, and I had a radical with the binomial, and I squared both sides, the police are not going to knock on my door and arrest me. It's nothing bad. It just makes the problem really, really difficult. So that's why my advice is, when it comes to radicals, you don't want to touch exponents until the radical piece is by itself. Let's do a few quick examples, and I'm just pulling these examples straight from your homework so you have fewer problems to do. Suppose you had like radical 3x plus 8 equals 17. Right. Now, a novice problem solver would probably think like this. Oh, gee, I see a radical here, so I know radicals and squares are opposites of each other. Don't write this down because I'm going to erase it. Oh, I'm going to just square both sides. And mathematically, that's legal. There's nothing wrong with that. It's just going to make an ugly mess because we're using we're using an exponent before the radical piece itself. If I were to highlight the radical part, this is the radical part. You do not want to do anything until that piece is isolated. So I hope visually we can see that our first step would be to minus the 8. That would be the smart path to go. Then we can go ahead and get this result here. That's a 9. And then lo and behold, I see that the radical piece is by itself. Now it is safe to use an exponent. The opposite of a square root, of course, we should know, is a square. When you square square root, the radical and the exponent cancel, leaving behind a regular 3x. And then it's just a one-step equation to solve now. Divide both sides by 3, go home, be happy. That's 27. Okay.
That's easy.
Yep.
No, I was just doing that. Yeah.
Now, take a look at the work that we did. Subtracting the 8, squaring, dividing. I mean, trust your math. You trust my math, I hope, right? I wouldn't say that about me personally because you don't know who I am as a person, so I wouldn't trust. I wouldn't trust myself with your guys' lives. But at least mathematically, I would not steer you wrong. We're pretty confident that 27 is the answer. Boom, 20. We did math, correct math, got a number, move on. And for the most part, you can do that. If you trust your mathematics, you trust your arithmetic, whatever answer you get is whatever answer you get. However, little footnote here. If your radical equation contains variables on both sides, you must check your answers. I mean, technically, you should check your answers 100% of the time, but we get lazy. So if you really wanted hey, Mr. Vo, what is truly the times I need to check my answers? It's when you have radical equations where there's x's on the left and x's on the right. The previous example that we did, we just the right-hand side of the equation was just a regular number. So whatever answer I got, I'm pretty certain that is the true answer. But when x's appear on both sides, you may get extraneous solutions. Something like this here. Say this example. Let's solve x equals the square root of 8 plus 2x. Again, the first thing I want to do is mentally highlight the radical. So if I highlight the radical here, square root of 8 plus 2x, hey, it's already isolated. I don't have anything else on the same side with the radical, so it's safe to go ahead and use an exponent right away. So I'll go ahead and square both sides, giving me an x squared equals 8 plus 2x. And then lo and behold, we have an x squared problem. So this is just a regular quadratic, so we have to utilize our past knowledge. To solve a quadratic, you get everything onto one side. So let's subtract the 8, subtract the 2x, giving us x squared minus 2x minus 8 equals 0. And then you solve it using what we've learned in the past. Solve it by factoring. If it's not factorable, use completing the square. And if you don't want to use completing the square, you have the quadratic formula. Fortunately, this example is factorable. So it's x minus 4, x plus 2 in any order that you want. Applying the zero product property gives us x equals 4 and x equals negative 2. But because my original problem had x's on both sides, we must check. So check x equals 4. A common mistake I see students making when they check their answers is they check them in the equation with the squares. You can't do that. You have to check it against the original, and the original did not have squares. So I'm going to check my answers against this original problem. So all you got to do is substitute the 4 in for the x. So we get 4 equals square roots, 8 plus 2 times 4, 4 equals the square root of 16, and 4 equals 4. That is good. So we keep our answer. Let's check x equals negative 2. So we get negative 2 equals the square root of 8 plus 2 times negative 2. Negative 2 equals the square root of 4. Negative 2 equals a positive 2. That doesn't make sense. That's bad. So we have to throw away this answer. We only have one answer, x equals 4. So that's just a little footnote there. If you have variables on both sides, you just got to take the extra step once you solve it to check your answers. You may have 2 answers, you may have 1 answer, you may have no answers, no solutions. Who knows? Okie dokie?
Yeah.
All right. The only way that this can get hard, I mean, it's not really difficult at all, I hope not, just inverse operations. The only way I can make this difficult is if I put more than one radical in a problem. Now, when I put more than one radical in a problem, remember this sort of third bullet point, the little one I asterisk, when there's more than one radical in a problem, that actually might not be possible. You might not be possible to isolate every single radical. So you're going to just have to move forward and make the problem difficult before it gets simpler. So problems with multiple radicals, it's sort of a things have to get worse before they have to get better kind of situations. Let's see an example here. Suppose I ask you to solve square root, and I'll do this one because this was a tricky problem for people in first hour. 4x minus 3 plus the square root of 10 minus 2x equals negative 1. Clearly, we have two different radicals here because the radicand, the stuff inside the radicals, are different. So you know how I said when I do a radical problem mentally, I sort of highlight the radicals. In this instance here, I'm going to highlight them using two different colors because they're two different radicals. So I have this radical here, 4x minus 3, plus, and I have this radical here, 10 minus 2x. Can't see? I'll take your word for it. So here, the individual radicals themselves are not isolated because, they're next to each other. So we got to move them apart. No, we need to isolate them. So it doesn't matter which one we move. Let's subtract the purple. Let's subtract the radical 10 minus 2x. So we get radical 4x minus 3 equals negative 1 minus radical 10 minus 2x. Here, the radical 4x minus 3 is happy. It's isolated. But you know what? The other radical, the radical 10 minus 2x, he's not happy because he has that negative 1 there. And you can go back and forth all day long, and you'll never, ever, ever be able to isolate both of them. So this is a, lesser of two evils. We can't isolate all of them, but at least we want to isolate one of them. So since the radical 4x minus 3 is isolated, we'll go ahead and use an exponent here. So the left part is easy because the radical and the square cancels, 4x minus 3. The right part will take some work. So I'm going to do some scratch on the side here. Do note that when you square a binomial, it's not as simple as distributing the exponent. That is a very, very common mistake students make, very easy place to get a problem wrong. You have to remember that squaring something is multiplying it by itself. So all I'm going to do is write him out twice and do good old-fashioned foiling. So negative 1 times negative 1 is a positive 1. Negative 1 times this radical is a positive radical. Negative radical times a negative 1 is a positive radical. And then a negative radical times a negative radical. Well, negative times a negative is a positive, so I can do that at least. And I hope everyone knows that when you multiply a radical by itself, the radical just disappears. So then all we get is 10 minus 2x. So go ahead and combine like terms. We only have like two pairs here. We have the 1 and the 10 are like terms. And this radical bit here is like terms with this radical bit. So we have 1 plus 10 is 11. This radical plus another radical is two of them, two radicals. And then the minus 2x is all by his lonesome self. So all of this scratch work is what should be on the right-hand side of our equation. So the right-hand side should equal 11 plus 2 rad 10 minus 2x minus 2x. You can see why this is a, quote, hard problem, because we squared it. We used the square. That should kill the radical. But guess what? We still have a radical term right here. This guy here, this annoying guy here, still needs to be taken care of. So before I can do anything, before I can solve this, I need to get that radical by itself. So we got to start over. Use inverse operations to get that piece by itself. So that tells us we need to get rid of the 11, get rid of the 2, get rid of the negative 2. Doesn't really matter what the order that we do it in. So let's subtract 11 from both sides. Let's add the 2x over to both sides. And then would everyone agree at this stage here, I would divide both sides by 2. This is where it sort of gets funky. I know this is going to suck, but this is the stage where you really need to use your brain. Normally, I would divide by 2. So I would look at the other side and ask myself, do both pieces, are they both divisible by 2? And the answer is yes, they're both even. So I'll go ahead and do that. But there may be examples where it's not possible. Let's pretend that this was a 3. It's not, but let's pretend. Oh, 3 goes into 6, but 3 doesn't go into 14. So if I were to divide by 3, I would have to work with fractions, which is not bad, but I know you guys hate fractions. So my little point is, if at any time you have to divide and it doesn't go in evenly, you can either deal with fractions or you don't divide and use exponents at this stage. It is okay to use exponents if you still have multiplication because the property of exponents allows you to distribute. However, in this instance, because everything's divisible by 2, let's just go ahead and get rid of that 2 by dividing. So that gives us a 3x minus 7 equals radical 10 minus 2x. Now we finally got the radical isolated. Go ahead and use an exponent one last time. And then it should turn into a regular good old-fashioned quadratic equation. The left-hand side, you just go ahead and expand, write it out twice in FOIL. That's going to give you 9x squared minus 42x plus 49 equaling 10 minus 2x. It's a quadratic equation. To solve a quadratic, it needs to equal 0. So let's move everything to the left-hand side. 9x squared. I'm going to add the 2x, which is a minus 40x. I'm going to subtract the 10, which is a plus 39, equals 0. And then you solve it by factoring. If you don't want to factor, you can clean the square or quad formula. Since the first number is a 9, it could be 1x and 9x, or it could be a 3x and a 3x. I don't know. You're going to try both ways. Let's break down 39. 1 and 39 and 3 and 13. The last symbol is a plus, so I'm going to think add. Which pair, when you multiply and add them together, gives you a 40? And I hope everyone can agree it's this guy here. 9 times 3 is 27. 27 plus 13 is 40. So the 9 needs to multiply with the 3 and the 1 with the 13. Since they need to combine to a negative 40, I know both of them will be negative. So I don't even bother with this guy here. So then that should be easy to solve. X would equal 3, and x would equal 13 over 9. Okie dokie? Everyone good? Are we missing anything? You have to check your answers. Why? If we take a look at the original problem, yeah, we had to do some moving things around, but take a look at the line right before we squared things. This was the line that we had before we squared things. Hey, I got x's on both sides of the equal sign. You got to check. So just take the extra second and check your answers. Can I assume we all know how to check? Can I just fast forward to it? All right, so to check, you plug it in to see if it works. Let me just spoil alert for you. You check the x equals 3. It's not going to work. You check x equals 13 over 9. It's not going to work. Do we have any other solutions to check?
No.
Nope. So the answer is no solution. Right. Yeah. All that for no solution. Yeah. But you didn't know it was no solution until you did the work. Yeah. The last example type I want to showcase is what happens when the problem hides the radical. What do you mean by hiding the radical? Well, recall, I think this was like lesson 1.2b or something. Recall that when we have a radical, a square root, cube root, fourth root, doesn't matter. that is the same thing as a fractional exponent. So they may hide a radical equation by not using a radical symbol at all, but instead using a fractional exponent. Now the idea is slightly different. To get rid of fractional exponents, you use a reciprocal exponent. It makes sense that I still need to use an exponent because fractional exponents are nothing but radicals in disguise, and exponents are inverses. But it just so happens that if your problem has a fractional exponent, you have to use a reciprocal exponent. Let's take a look at an example here. Let's say I wanted to solve 46 equals negative 2 plus 3 times the quantity x minus 19 raised to the 2/3 power. At first glance, you're going, oh, this is just a regular equation. There's no radicals. But since I noticed the exponent is a fraction, that is, in a sense, a radical part. So as before, mentally, what I do is I highlight the radical parts. It just so happens that the radical part comes in exponent form. X minus 19 to the 2/3 power. When you highlight the radical part, I hope it's easy to see that, oh, our goal is to get rid of that negative 2 and to get rid of that 3. So to get rid of the negative 2, we're going to add 2 to both sides. 48 equals 3 parentheses x minus 19 to the 2/3 power. And then to get rid of that 3, we're going to divide him out. So 48 divided by 3 is 16. Now that the radical part is isolated, yes, I know it doesn't look like a radical, we can go ahead and get rid of it, and the idea was to use a reciprocal exponent. So if I want to get rid of an exponent of 2/3, I'll use an exponent of 3/2. 3/2. So we end up with 16 to the 3/2 power equals x minus 19. Now all we have to do is simplify that 16 to the 3/2 power. And again, I think this is like 1.2a or 1.2b. So here's some scratch work. 16 to the 3/2 power. Remember, the idea is that the denominator is your radical and then the numerator is your regular exponent. So since the denominator is a 2, this means square root. So this is square root of 16 cubed. And I hope that's something we can do in our heads. Square root of 16, 4 cubed, 64. We got to be careful here. This was the scratch work, but this was the actual problem, right? What did the problem tell us? What problem, or what was our original instructions? To solve an equation, right? Our original instructions were to solve an equation. And what did we do right here? Simplify, but what math thing did I do here? I did the radical. I simplified doing the radical. What radical did I use? Not the 3. 3 is the exponent, but the radical part is a square root. I'm using a square root in the process of solving an equation. Remember that tip before, that when you're solving an equation, anytime you use an even root, your result will be plus or minus. You cannot forget that even in these situations. So we used a square root in the context of solving, so the result will be plus or minus 64 equals x minus 19. And then you go ahead and solve it by adding 19. X equals 19 plus or minus 64. Since my answer does not contain any special symbols, like a square root or something, I expect everyone to go ahead and split apart the answers. So x equals 19 plus 64, x equals 19 minus 64, so you can get two separate answers. That's 70, 83, that is negative 50, 45. Right. Yes, it would be good practice to check our answers, but since the original problem only started with one x, and I'm pretty confident that we did our arithmetic correctly, it's safe to say that both of those are our answers. So that's radical equations in a nutshell. You don't need any special techniques, it's just inverse operations, but there are some extra considerations into play. Don't use an exponent until the radical is by itself. If there are multiple x's, you should check your answers. And if they hide a radical in a fractional exponent, just use a reciprocal exponent. Okie dokie? That's it. That concludes our solving equations adventure. That is 1.5D. We're gonna have the same thing.
Can we go faster? Achoo, achoo. Achoo, achoo.